Welcome back to AI.Code.Cast. Today, we're going to do a deep dive into a coding problem that's really going to make you think. And this one's called maximum value at a given index in a bounded array.
It sounds kind of abstract, I guess, when you first hear it, but maybe imagine like you're running a project with a fixed budget.
Yeah, like a limited amount you can spend.
Right, exactly. And you have to allocate these resources across all these different tasks.
Yeah.
The catch is that you absolutely have to like maximize the resources for one specific task, and that's what we call the index in this problem.
Okay, so like one of these tasks is the most important. You got to put as much as you can towards it.
Yeah, and at the same time, you got to make sure that like your overall spending stays within the budget.
Right. So that overall budget, that's our maximum in the problem.
Exactly.
Okay, so that makes sense. And that's already kind of a tricky problem. But then we have this extra little constraint, right?
Yeah, so you can't just like dump all your resources into that one important task.
Right. You can't just go all in.
Like the allocation that you give to like tasks that are next to each other, they can only be like one different at most.
Oh, so they have to be pretty similar.
Yeah, so it's really all about finding this like sweet spot between maximizing for a specific element, but also making sure everything is balanced.
Hmm. So it's kind of like if you were building, I don't know, like a Lego tower or something.
Yeah.
And there's a certain spot you want to be the absolute highest, but you still need to like have a solid base
Right.
to make sure the whole thing doesn't fall over.
Exactly. You can't have just a single tower in the middle with nothing around it.
Exactly. You need those slopes to be able to get to that top point.
Oh, sure.
So, okay, this is starting to make a little bit more sense, I think. But how do we even begin to think about solving something like this? Like if I'm coming at this for the first time, I might think, okay, well, can I just like try every possible value for my target task and see if it works?
Oh, yeah, that's definitely like a common first thought. And that's basically the brute force approach, right?
Just try everything, see what's...
Just try everything until you find the right answer.
Yeah.
Yeah. But the problem is, like, what if you have a project with, like, tons of tasks and just a massive budget?
Yeah.
Like, trying every single combination would take forever.
Yeah, you'd be there all day.
Yeah, and especially, like, in the real world, when you're dealing with, like, big data sets, it's just not going to be efficient.
So brute force is out the window.
Yeah. Brute force is not going to work here.
But what's like the key insight that can kind of lead us towards a more efficient solution? Like,
Yeah.
what's something special about this problem that we can exploit?
Okay, well, let's think about it this way. If we can actually achieve a certain value at our target index, right,
Okay.
then anything smaller than that has to also be possible.
Oh, that's interesting.
Right. So that actually means that this problem has a property that we call monotonicity.
Oh, I see where you're going with this. If
Yeah.
we have this monotonic property, then maybe we could use something like binary search.
Exactly.
We wouldn't have to check every single value. We could strategically just like zoom in on the best one.
Yeah. It's all about being efficient.
Exactly.
But before we just jump into binary search, we need to have a way to efficiently determine if a given value at our target index is even possible in the first place.
Right. We need to make sure that like if we pick this value, we can actually create a valid distribution.
Yeah. And make sure we don't go over budget.
Right. So, okay, let's say we pick a value V for our target index. How do we figure out, like, quickly if it's even possible to make that happen?
Okay, so this is where the like greedy part of the solution comes in.
Okay.
So remember, our goal is to maximize the value at the target index, right?
Mhm. Yeah.
So to give ourselves the best chance of staying within that max sum, we want to try and minimize all the other values.
Yeah.
So basically, we're trying to make like a hill shape with the target index at the top,
Okay, I can kind of picture that.
and then like decreasing as smoothly as possible on each side.
Yeah, it's like our Lego tower again, right?
Exactly.
You want the highest peak, but you want to use as few blocks as possible on the sides to get there.
All right, you want to save all those blocks for the peak.
Exactly. Yeah, okay, but how do we actually calculate what that minimum sum would be, like quickly, without going through the whole array, like element by element?
All right, so this is where a little bit of math comes in handy.
Oh, no.
Because we're decreasing by one on each side of our target index, right?
Yeah.
The values are actually forming something called an arithmetic sequence.
Okay.
And luckily, there's a nice formula to calculate the sum of an arithmetic series.
Oh, so we're using some high school math to avoid doing a bunch of calculations.
Yes, exactly.
So this formula lets us quickly figure out, okay, what's the minimum possible sum if we have this value at the target index.
Exactly.
Okay, and now that we have that, we can finally bring in our binary search.
Right. So now instead of testing every single value,
Yeah.
we can use binary search to quickly narrow down our search space.
Okay, I like it.
So actually, why don't we walk through an example from the source material? So let's take example 1, where n has 4, the target index is 2, and then our maximum is 6.
All right, so n is 4. That's
Yep.
the size of our array index is 2. That's our target. And our max sum is 6.
Yeah.
Okay, got it.
So initially, our search range for the value at that index would be from 1 to 6.
Right, because it could be as small as 1 or as big as 6.
Right, and the middle of that is 3.
Okay.
So let's imagine we set our target index to have the value 3.
Okay.
Now, using our greedy approach and that formula we were talking about,
Yeah.
we would calculate the minimum possible sum for the array
Okay.
with a 3 at the target index.
Okay.
And the array would probably look something like 1, 2, 3, 2.
Okay, and if you add all those up, the sum of that is 8.
Right, and that's bigger than our maximum, which is 6.
Yeah, so 3 is too big.
Yeah, exactly. 3 is too high for our target index. So now we would adjust our search range. We'd focus on everything from 1 to 2.
Okay, so we're going smaller.
Yeah, and we just keep repeating this process, right?
Okay.
So we check the middle value, calculate the minimum sum, and then adjust our search range until we find the best one.
And I'm guessing in this example, we would eventually get to the value 2,
Exactly.
which would give us the array 1, 2, 2, 1.
Yeah, which meets all of our conditions.
Perfect.
So that's pretty cool, right? We found the maximum value for our target index, and we stayed within our budget.
Yeah, that's awesome. And it seems like this combination of the greedy approach and binary search is like a really efficient way to do this.
Yeah, it's super efficient, and I think it's a really elegant solution,
Yeah.
but it is important to remember that this is really relying on those specific constraints that we have for this problem.
Okay.
Like, if we were to change those constraints even a little bit, like say we allowed the difference between adjacent elements to be bigger,
Yeah.
then our approach would probably need some tweaking.
Okay. Yeah, that makes sense.
Yeah.
So we've really leaned into these specific rules to come up with this approach.
Exactly.
Okay, cool. So we've got this binary search approach, but now I'm kind of curious, could we have used a different search algorithm here? Like, is binary search really the best fit because of that monotonic property that we talked about?
Yeah, that's a great question. It's always good to think about alternatives, but I think binary search is really powerful here, specifically because of that monotonic property.
Yeah, if it works for a value die.
Right. Then it's got to work for anything smaller than dies, too.
Yeah, and that's what lets us get rid of half of the search space right away.
Yeah, exactly. It's like when you're playing that number guessing game,
Oh, yeah.
you know, where they say higher or lower.
Yeah.
Each time you make a guess, you're getting rid of half of the possibilities.
Right, exactly. So it seems like binary search is really the way to go here.
Yeah, it's really perfect for this situation.
Okay, I'm convinced binary search it is. But now let's get into the actual code a little bit.
Okay.
Like if we were to sketch out the pseudo code, what would be the main steps for this solution?
Okay, let's break it down. So first, we're going to need like a helper function
Okay.
to calculate that minimum sum for a given value at the target index.
Right.
So let's just call this function calculate minimum sum. And it's going to take the target index, the value that we're trying at that index, and then the total size of the array.
Okay, so it needs to know where we are, what value we're trying, and how big the array is.
Exactly.
Yeah.
And inside that function, that's where we're going to use that formula.
Right, the arithmetic series formula.
Exactly, to quickly calculate the sum of everything.
Okay.
But there is like one little detail we need to be careful of.
Oh, okay, what's that?
So what happens when like those decreasing sequences on each side of the index?
Yeah.
What if they hit the edge of the array?
Oh, right. So what if we end up with a bunch of ones at the beginning or the end?
Yeah, exactly.
Yeah.
We need to like handle those edge cases where the formula might not work perfectly.
Okay, so we need to make sure our function is smart enough to handle that.
Exactly, yeah.
Okay, so we've got this calculate minimum sum function. It takes the index, the value we're trying, and the size of the array, and it spits out the minimum sum for that configuration.
Right.
And now we need to hook that up to our binary search, right?
Okay, so now for the main part, the binary search itself.
All right, let's do it.
So first we're going to initialize our search range.
Okay.
So the left boundary is going to be 1 because we're only dealing with positive integers here.
Makes sense.
And the right boundary is going to be our max sum.
Okay, so the biggest it could possibly be.
Exactly.
Yeah.
So we're basically saying our answer has got to be somewhere in this range.
Right. Between 1 and max sum.
Exactly. And then we're going to go into our binary search loop.
Okay.
So as long as our left pointer is less than or equal to our right pointer, we keep searching.
Okay.
And in each step, we're going to calculate the midpoint.
So that's like the average of the left and right.
Exactly. And that midpoint, that's our current guess for the target index value.
Okay.
And then we call our calculate minimum sum function.
Right, using our index, our midpoint value in the size of the array.
Yeah, exactly. And that'll give us the minimum sum if we use that midpoint value.
Okay, and then what do we do with that?
Okay, so now we got to make a decision right. So if that minimum sum is less than or equal to our max sum, that means that our midpoint value is possible.
Okay.
So it could be the answer, but we could also maybe find something even bigger that still works.
Oh, interesting.
So we update our best answer so far to be that midpoint, and then we move our left pointer up to midpoint plus 1.
So now we're only looking at the bigger half.
Exactly.
Okay.
But what if that minimum sum is bigger than our max sum?
Then we know our midpoint's too big.
Right, we got to go smaller.
So we move the right pointer down.
Yeah, exactly, to midpoint minus 1. So we're only looking at the smaller values now.
Okay, so we just keep doing this over and over again, right?
Yeah, we keep checking the midpoint, calculating that minimum sum, and then adjusting our search range.
And the search range gets smaller and smaller.
Exactly. And eventually that left pointer is going to pass the right pointer.
Oh, and that means we're done?
Yeah, exactly. That means we found our answer.
And that answer is the biggest possible value for our target index that follows all the rules.
Right. It's the best we can do.
That's pretty slick. So not only is this solution efficient, but it's also like really elegant in how it works.
Yeah. I agree. It's a really nice approach. And by combining that greedy strategy with binary search and a little bit of math, we've managed to solve what could have been a really tricky problem.
It's like we've got this secret weapon in our coding toolbox now.
Exactly.
But I think it would be helpful to connect this back to the real world a little bit.
Yeah.
Like we started with that analogy of resource allocation.
Right.
So how could understanding this algorithm actually help someone in a practical setting?
So like imagine you're working with a limited marketing budget, right?
Okay.
And you have to split that budget across a bunch of different campaigns.
Yeah.
But you know that like one specific campaign is super important.
Like that's our target index.
Exactly.
That's the one we got to put as much money towards as possible.
Yeah, you want to give it the best chance of success. And this algorithm is basically giving you a way to figure out like, okay, what's the absolute maximum I can invest in that critical campaign?
While still making sure the other campaigns can run.
Exactly. It's all about balance.
Right. You don't want to completely neglect the other ones.
We got to keep everything going.
Exactly. Okay, so that's a really clear example with marketing.
Mm.
But I feel like this could apply to like tons of different scenarios.
Oh, yeah, for sure.
It's like anytime you have some limited resource that you have to split up.
Like project management or time scheduling.
Right, like how much time should I spend on each task if I have a deadline?
Exactly. It's really useful for any kind of optimization problem.
And I think it really shows how powerful it can be to like combine these different techniques.
Yeah.
We took this greedy strategy, we added in a little bit of math, and then we brought in the efficiency of binary search. And we got this really nice, elegant solution.
It all works together perfectly.
Exactly. And I think that's like a really important takeaway for our listeners. Understanding the structure of the problem can really lead you to the best solution.
It's not about memorizing every single algorithm.
Right.
It's more about like developing that analytical thinking.
Like that ability to see the patterns.
Exactly. So you can figure out what approach is going to be the best.
So today, we didn't just solve this one specific problem.
Yeah.
We also gave you a really powerful strategy that you can apply to all sorts of challenges.
Right. This combination of greedy thinking, searching, and a little bit of math.
It's like a coding superpower.
And we want you to think about like, where else could you use this?
Yeah, what other problems can you solve with these tools? Let us know.
Yeah, we'd love to hear your ideas.
That's all for this episode of AI.Code.Cast. Keep those coding brains buzzing, and we'll catch you next time for another deep dive.